Hello, in this video I'll be talking about what you'll be doing in experiment 6, which is centered around Hess's law. In this experiment, you're going to carry out a calorimetric experiment and measure the enthalpy changes associated with 3 different chemical reactions. And with this, then you can see how closely they conform to Hess's law. That means that in today's lab, you'll get practice in the rapid mixing necessary in calorimetry, and practice in using the weigh balance, being very skilled and accurate in getting masses, and the careful transfer of materials. This should help you understand the idea of Hess's law and the idea of state functions, that it doesn't matter on the path, all that matters is the final energies and the initial energies. And then finally, we'll be doing a lot of exothermic reactions today, and you'll have confidence in understanding the idea that the heat released from a reaction that's then transferred to a solution causes that solution temperature to change, and you can then relate the temperature change of a solution to the enthalpy of a reaction. So today's all about calorimetry. We can use calorimetry to determine the enthalpy of a reaction. And remember, enthalpy is the energy that's transferred as heat. And we'll use a coffee cup calorimeter. So it's kind of low tech, but it's effectively just a styrofoam cup, and you put that inside of another container, either a glass beaker or another styrofoam cup, and that helps prevent any heat loss from the reaction. In this aqueous solution, the reaction occurs, and there's simply a thermometer that reads. You won't have a real thermometer. You'll actually have a probe that can monitor the temperature a little bit more accurately than you could with the thermometer that's shown here. But the setup is basically this. You have your reaction inside of a styrofoam cup, and then there's another vessel to help keep the heat in, and all you're doing is measuring the temperature change. And we're doing this because what we want to know is the enthalpy of the reaction. That's what we're after, and the way we're going to do that is we're going to consider the heat of the system. So the delta H of the system is going to be equal to the enthalpy of the reaction, and that energy that's either, for us, it's always going to be the energy that's given off from the reactions, but no matter what, the energy from the reaction is then transferred to the heat or to the solution, and that means that since it's going to be a simple transfer between the reaction and the solution, that the enthalpy of the system is going to be 0. So with no change in enthalpy of the system, what we're going to consider is that for us, if the reaction is exothermic, and this is then a negative number, that's all transferred to the solution, the temperature will raise, and that means that this is then equal but opposite in sign to the enthalpy of the reaction. So what that means is that in order to determine the enthalpy of the reaction, it's going to be, again, opposite sign of the enthalpy of the solution. And as you learn in class, the enthalpy of the solution is simply the specific heat capacity, which you'll find in the manual because it depends on the solution that we'll use. The mass that you use inside of the calorimeter, and then the change in temperature. And this is what you'll actually measure, is the final temperature and the initial temperature. And as I said, we'll be doing a couple different reactions, and the specific heat capacity isn't always equal to just the specific heat capacity of water. So you'll have to check to see which value you should be using in each step. So all of these experiments today, beyond just determining the enthalpy of each reaction, is meant to verify Hess's law. So in these reactions that you'll be doing in the experiment, you'll be mixing aqueous solution of sodium hydroxide with a solution of hydrochloric acid and performing the neutralization reaction to make the salts, sodium chloride, and water. You'll also see the heat of dissolution, which is the process in which, in this case, sodium hydroxide dissolves into water. And this will cause heat. If you ever do this, if you remember from the titration lab, the solution actually gets warm when sodium hydroxide dissolves. We're going to do a third reaction where you'll do the dissolution of the sodium hydroxide, starting with the solid, not the solution, and then putting that into a solution of hydrochloric acid to do the same neutralization reaction. Now, the neutralization reaction is exothermic, the dissolution of sodium hydroxide is exothermic, and equation 3, which is both the dissolution and the neutralization is also exothermic. And if you haven't noticed, equation 3 is simply the summation of the first two equations, where you're not only doing the neutralization, but you're also including the energy that's released when sodium hydroxide dissolves in water. So this is what we're going to be doing today, is we're going to be considering the fact that Hess's law says that the enthalpy of the third equation should be the exact same as the enthalpy from the first equation plus the second equation. I'll keep calling this an equation, maybe even a reaction, but this is more accurately described as a process where we're dissolving the sodium hydroxide. But the idea in the lab is that you'll be finding the enthalpy of the neutralization of sodium hydroxide and hydrochloric acid. You'll then consider the enthalpy of the dissolution of sodium hydroxide, and then you'll consider the enthalpy of the combined reaction. And again, this enthalpy should be equal to the enthalpies of the first two combined. It's also important to note that in kind of the real lab setting, you're never going to have perfect molar ratios of everything. So you always have to be sure what the limiting reagent is in each case. So in the sodium hydroxide case, it's fairly easy. You don't have to consider what the limiting reagent is because it's only sodium hydroxide dissolving. But in each case, you have to consider is the sodium hydroxide limiting or is the hydrochloric acid limiting. So whatever enthalpy you detect in your reaction, you're going to relate that to the number of moles that had reacted. So it's important to check and always be sure that when you relate the enthalpy that you see, that you always consider what the number of moles that actually reacted in your calorimeter is. So for the first equation, we're doing the neutralization of sodium hydroxide and hydrochloric acid. You're going to mix equivalent volumes of roughly equivalent concentrations, and that should effectively be 1-to-1, complete 1 mole to 1 mole ratio. Make sure you actually write down the concentration in the bottle, because you might not get these exactly, but that's what we expect to give you. And during this process, there's important things you need to write down. And this is consistent no matter what reaction we're doing in the calorimeter. The first thing you want to do is you want to get down the mass of the insulated cup and the stirring bar, and that's going to be kind of your, that's just the reaction of the vessel, the mass of the vessel. Then you'll add, in this case, the sodium hydroxide solution first, and you can get the mass of the cup plus this first solution. Then you'll set up your calorimeter and you'll start getting those initial temperatures because you want to get an idea about what the initial temperature is. And to be sure you have a good and accurate reading and that the temperature is stable, you're going to monitor this for a little while before you start the reaction to make sure the temperature is consistent. Then you'll add the next solution. In this case, you'll add the hydrochloric acid solution, and then you'll start measuring the temperature after that addition. Remember, again, we want this to mix well and react quickly so we can see that temperature as soon as possible. And we're going to monitor the temperature over time to make sure that we get that we can get as much data as we can. Then, once it seems like you've got enough temperature data, then you can then take that cup that has, again, the cup has the stirring bar, has the sodium hydroxide solution, and the hydrochloric acid solution. Once you're all done getting temperatures, then you can get the mass of the cup with everything in there. So it's important to note what the total mass is, because you'll use that for your specific heat capacity equation. Now I kind of want to dig into this point here, measuring the temperature after the addition of the hydrochloric acid solution, because what we hope to see is what I've shown here is kind of this perfect set of data. I've shown that maybe there can be some bouncing around in the numbers from the thermometer, and that's expected. It's okay if there's some noise there in the data that you get. But the idea is that the second that you add in this case, the hydrochloric acid solution, in a perfect setting, it would react completely and it would react instantly. And then you can easily see what the initial temperature is by plotting a straight line and seeing what that average value is, and then doing the same thing with the final temperature. And from this, then you could find out exactly what that delta T is. The problem, of course, is that you will not get perfect data. One is that it's going to be quite difficult to get as many time points as I've shown here, and as well to get time points in the region around when you're doing the reaction. The other thing to note as well is that the reaction does not occur instantly. It will take time, and the temperature will rise over the course of the reaction, and eventually it should get towards the temperature that you need, but it won't be instantly. So you need to monitor for a while and wait for that temperature to kind of, normalize. Another confounding factor is that this assumes that the calorimeter is perfect and there's no heat loss, that whatever energy is whatever energy due to the reaction occurs, that it transfers to the solution and it stays there, that it does not escape the system. The problem is that it never is going to be, you're not going to have a perfect calorimeter. So you'll cause your reaction to start, that will then release some heat into the solution, that'll cause the solution to heat up, and then over time that heat will dissipate outside of the system, so the temperature is going to fall. So you're never going to actually reach the temperature that you should. What we're going to do to try to get around that is we're going to consider the fact that at some point the final temperature would have been reached, and now the reaction is completely over, and the change in temperature is simply just due to the cooling, the loss of energy over time. So what we're going to do is we're going to consider at what point does the curve stop, and now it could be fit to a straight line. So if you fit that to a straight line, you can then extrapolate back to when you added the second solution and make a good guess about what that final temperature should have been if it had reacted instantly and if it was not losing temperature slowly to outside of the calorimeter. So this is what you're going to do in the experiment is you'll get the mass of your cup, you'll add the solution, get the mass of those combined things, start getting the temperature so you can get a good accurate estimate of the initial temperature, and then you'll get some points of the temperature over time. And you want to wait for a while to collect some good data. I would say probably at least 10 minutes, but we'll look to see how long it takes. And just measure and write down all of these temperature points over time, and then at the end you can extrapolate to find out what the true final temperature of that reaction would be. So that's the nitty-gritty about how to do the experiment, but now going back to the general idea, once you've determined the heat responsible for the reaction of aqueous sodium hydroxide and aqueous hydrochloric acid, we'll then determine the enthalpy from the dissolution of sodium hydroxide. For this one, you're going to dissolve enough sodium hydroxide into 100 milliliters of water to make a 1.25 molar solution. So be sure to have this calculation done and ready before we start the lab. So the idea is that you'll have your calorimeter cup, you'll get that mass, you'll add 100 milliliters of water, you'll get that mass, and then you'll have weighed out enough sodium hydroxide to make what you expect to be a 1.25 molar solution. And from there then you can estimate the moles, and with that then you can then calculate the enthalpy of the dissolution. You want this to be very quick because the faster it is, the more accurate your data will be. Because again, remember, we want the reaction to occur as quickly as possible so we can get a good estimate on the final temperature. If you remember from the titration, it takes a while for those pellets to dissolve, but it goes much faster if it's a fine powder. So what you're going to do is you're going to use a mortar and pestle to grind up those sodium hydroxide pellets. We'll try to demonstrate it in the lab, but you grind slowly, carefully, and with force. You don't smash because you don't want sodium hydroxide pellets to be flying around. And as I said before, it's run effectively in a similar way. You'll get the mass of the cup, the mass of the solution, you'll get the initial temperature, you'll start monitoring the final temperature for some time, and then once it seems to be done, then you can get the mass of the full cup. The goal is to get 3 trials. If you only get 2 trials in for each, that's okay. For each one, I would probably do 2 trials of each, and then if you have time, go back to get a 3rd trial to get better data. but you do want to get enough information to get an average and a standard deviation for each step. Finally, for the third reaction, we're going to do the dissolution and the sodium hydroxide hydrochloric acid neutralization reaction. So you're going to add 50 milliliters of water, 50 milliliters of the acid solution, and then you'll dissolve just enough of the sodium hydroxide to mostly, but not entirely, neutralize the HCl. This way we can be sure that the sodium hydroxide is our limiting reagent, and you can calculate the number of moles from the sodium hydroxide. And again, you want to know how much you should be adding, so do this calculation before class starts. And as I said, the goal is to do 3 trials. Start off with 2 and then revisit to do the third if you have time. And again, it's run very similarly. You get the mass of the cup, you add the water and the hydrochloric acid, you get that mass, you start measuring the temperature, add the sodium hydroxide, and then measure the temperature for a long enough time that you get a good set of data, and then get the mass of the cup with everything in it after the reaction is finished. So as we said, this is a demonstration of Hess's law. And Hess's law states that the enthalpy change of an overall process is the sum of the enthalpy changes of each of its individual steps. So consider the fact that the first equation represented a neutralization reaction, the second one is the dissolution, and the third one is the combination of the dissolution and the neutralization. So what you're going to do as part of your lab report is calculate again those change in enthalpy values for the first 2 steps, and then realize that it should be equal to the enthalpy change of the third step. And this is how you can demonstrate that Hess's law still holds for your system. So this is the goal of the lab, is to determine each of these values, the change in enthalpies for equation 1, equation 2, and equation 3, and see how close you are to having these 2 sides being equal. And I'll say it again, remember the fact, we're thinking of the fact that the enthalpy of the system should be 0, because all of the enthalpy that's released in our case from the reaction should then be transferred to the solution. And we can determine the enthalpy of the solution because we'll know the specific heat capacity, and again that's given in the manual. We'll know the mass of the solution, and we'll know the change in temperature from initial to final, and we'll guess the final by extrapolating the data. So now that you know everything for what the purpose of the lab is and what you'll be using, what important numbers you should be writing down during the lab and how you use that in the lab report, I want to go over some safety concerns for today. There's a lot of acids and bases today, so be very careful with any solutions you use. If there's any strong acid spills, remember to use sodium bicarbonate to neutralize those to make them safe to pick up and use. Always be wearing goggles and lab coats, and then always wear gloves whenever you're using the concentrated acid solutions. Again, obviously no flip-flops, always closed-toe shoes, wear pants, and again, no gum chewing. And then finally, I will stress again that if you get a third trial, your numbers will have a better average and standard deviation. It's important that you have good trials for each of them, at least get 2 for each step. The goal is to get 3, and if you have time and it seems like you can benefit from it, you could even do a 4th trial to kind of tighten up those numbers. Okay, I hope all that makes sense. Calorimetry is kind of a fun, interesting idea, and it's interesting to show how these basic ideas of the very fundamentals of chemistry and physics, the first law of thermodynamics, can be demonstrated with just a coffee cup. So I hope that everything makes sense, and I'll see you in the lab.